Now let's talk about the section 6.2. One-to-one functions and the inverse functions. Okay, so first we want to define what a function is, a one-to-one function. We know what is a function. A function is a correspondence or a map so that for each input there is a unique output. Okay, so for one input there is a unique output. So that is a function. So for example, if we have a school with many students, at one moment we can measure their height. Okay, so for each student there's only one height, so this is a function. So we have a height function. For the height function, what is input? Input means each student. Whenever you get one student in, and then you measure the height, right? Input a student. What are outputs? Outputs are heights of those students. Right? So this is input output. And sometimes we don't have function. For example, we ask what colors each student likes. Okay, so we can ask, do you like the red color, or what color do you like? You may like red color, or you may not. You may like orange color. You may like the red or orange and the orange color. So we cannot just. I mean, I don't ask you to get your the most favorite color. I just ask you a very general question: what color do you like? Then we cannot have this answer as a function because it is not unique and the output is not unique. Like you can have like 10 favorite colors. Well, that's possible, right? So we like a lot of stuff. If you don't want to put color, you can like what kind of a video game you like. So you may like this video game or that video game. There's many choices of video games. So for this is not, for this type of a question, we do not have function because every student may have multiple choices. Okay, so function just means whenever you have an input, you will get an output. You have an input, you will get output. You have an input, you may get output. For example, if a height, two kids may have the same height. So it's possible to get the same result for different input. It's allowed. But for one input, there's only a unique output. Okay, this is a function. Uh, there's another question. For example, what is a student number? A student number of students. Then for each student, you will have a unique number. Two students will not have unique number. And this kind of stuff, the importance is that whenever you know the student, you can get the number. And when you get the number, you will have the student. So that is what we call one-to-one. All right? So one-to-one just means those two things. You don't have two arrows targeting the same one point, one object. Okay? Now let's see the definition. A function. One-to-one is a special property of a function. If you do not have a function, of course you will not discuss one-to-one. So it's a property function. A function is one-to-one, or if you want, you can just write this way: 1, 1, 1. It is a function is one-to-one if any two different inputs correspond to different output. Okay, different input, different output. And in other words, if x1 is not equal to x2, then the output, when we say a function, normally we use this f to represent this this question or this function. Then fx1 is not equal to fx2. Two different input implies two different output. So this is a one-to-one function. So this one is one-to-one, and this one is not one-to-one, because this is 2-to-1. Like you see here, at least here, this is 2-to-1, not a 1-to-1. Okay, so if we, well, this is a very simple question. We can just draw the arrows and get the answer. And sometimes if we get the graph of a certain function, for example, we may have some graph like this, or we may have some graph like this. For this graph, you see, if we draw a horizontal line, then horizontal line means they have the same height. They have the same y value. Okay? Horizontal line implies the same y value. For the same y value, you will have two corresponding input x1, x2. Of course, this does not satisfy the definition of a one-to-one function. So this is not one-to-one. In this one, for each y, there's only one x possible. So this is one-to-one. And because we always draw horizontal line to check if the function is a one-to-one or not, so we call this horizontal line test. Horizontal line test. If every horizontal line intersects the graph, so this horizontal line test is used when you have the graph of the function. If you don't have the graph, of course you will not use horizontal line. Graph of a function f intersect in at most 1 point. At most 1 point, then f is 1 to 1. So this situation cannot happen. It may intersect at 1 point. It may not intersect at 1 point. For example, I can give you this example. The graph looked like this. This is a so-called horizontal asymptote. If you draw a horizontal line in this place, it's outside the range. Of course, it does not intersect the graph, but it's okay because the intersection is 0. Here intersection is 1 or 0. They are covered by this condition at most. But this one, it has 2 intersection points, so it's not 1 to 1. Okay? Okay. When you have the graph, you can use this way. Remember that we also have a type of a function. So for example, we have given f. The function is determined by what? By the pairs, like -2, 6, -1 and 3, 0, 2, 1, 5, and 2, 8. If you have such given function, then you want to determine the 1 to 1, if it is 1 to 1 or not. You just check if the same is f1 to 1. The question is f1 to 1. All right, so let's see. In order to determine this type of function to be 1 to 1 or not, you just check the output. This is output. If the output does not repeat, you see this 6, 3, 2, 5, 8, they're all different. So 6, 3, 2, 5, 8 are different. F is 1 to 1. Because of course those are the input. The input must be different. For one input, there's only one output. This is a function at least. So you have different input. You should never have the same output. If you have the same output, not 1 to 1. If it does not have same output, it is 1 to 1. All right? So this is another way. Okay. And two simple case from the so-called horizontal line test is that what is this graph? This graph is always going up. So this is an increasing function. An increasing function on an interval I is always 1 to 1. Okay? When we say increasing, what is the increasing? Increasing means x1 less than x2. You have the relation about input. It will imply fx1 less than fx2 have the same, those two inequalities have the same direction. Then this is an increasing. A decreasing function on an interval, on an interval I is always 1 to 1. So what is decreasing? Decreasing means smaller input, x1 is smaller, but it will give you the larger output. So this is a decreasing. Increasing is like this. From left to right, you always go up. Decreasing is opposite. From left to right, you always go down. But either way, you go up or go down, you use the horizontal line to intersect them. The intersection point is at most 1. There's at most 1 intersection point. Okay, so increasing, decreasing function are always one-to-one function over the interval. All right, so we gave the definition of a one-to-one function. Here, the definition of one-to-one function: different input, different output. And then we have the horizontal line test. And then we have this example about the determination of a one-to-one function for this type of a function. This type of a given function. Just check if you have the same output or not. If all the outputs are different, then it is one-to-one. If some of them are repeated, then it is not one-to-one. And then we also have two special cases. Increasing function is always one-to-one. Decreasing function is always one-to-one. All right? So remember, what is the advantage of one-to-one function? So check here. Assume we have student number for each student. You have a student, you got a number, the unique number. Of course, if you know the student number, you can go back and identify the student. That is the purpose of the student number. And this go back process from student number to student, this is called the inverse of the original function. The inverse of the original function. So from the one-to-one function, we can only discuss the inverse from the one-to-one function. Because, for example, if it's not a one-to-one, like this one, you want to go back, which one do you choose? We don't have a rule. We don't know which one we should choose, right? So that's a abstraction. So we can find, or we can define inverse function only for one-to-one function. The inverse function is like to identify student based on the student number. So suppose that f is one-to-one. So this is a hypothesis. Then to each x in the domain of f, so first of all, it is a function. There is a unique y in the range such that y is equal to fx, right? Y is equal to fx. And this is up to this point, that's a function. And for each y in the range of f, there is exactly one x in the domain of f, so that y is equal to fx, right? That's just another way to say it, because this step we use f is a one-to-one. Up to this point, f is a function. Okay? So from x to y, that's always a function. But if you want to go back, you need additional condition, the one-to-one condition. Okay, then we will say the correspondence or the function from y 2x is called the inverse function of f, and denoted by f negative 1. F negative 1 does not mean the reciprocal, it means the inverse of f. Okay? F negative 1 is the inverse of f. So, for example, this is a definition, very long. For example, let's recycle this example. Given this function f, we have negative 2, 6, negative 1, 3, and 0, 2, 1, 5, and 2, 8. Then what is f inverse? F inverse, now we are going to first start from the output, original output. 6 is output. Then its corresponding input is negative 2. You're going to exchange the x, y position. Here it is a 3, negative 1. Here it becomes 2, 0. Output is a y. This is a y. This is x. Given y, I want to determine x. Given y, I want to determine the x. And given y, I want to determine the x. So this is the inverse function of the original function. Okay, so whenever you talk about inverse, you actually already have one function, and then you can talk about the inverse. If you do not have function, then there's no inverse. This is a new function. Okay, this is a brand new function. It is inverse to the original f. They are actually paired. They're actually paired. Okay, so exchange x and y. From x to y, that is f. From y to x, that is f inverse. And you can see that this is a domain of f. This is a range of f. But for f inverse, this becomes a domain, and here becomes a range, right? Right side becomes a domain of f inverse. Left side becomes a range of f inverse. So we get two relations. The domain of f, here is a domain. It becomes, you see, that's a target of f inverse, is a range of f inverse. And the range of f becomes a domain of f inverse. They interchange domain and the range. Interchange domain and the range. Okay. Another property, if you have a student use a student number function, you can get the student number. And then use a student number, the same student number, you can go back to get the student. So for each x in the domain of f, each student, you apply the function, you get the student number, and you apply the inverse function, you go back to the student, right? For each x in the domain of f, you apply f and then f inverse, you actually go back. It's like you go right and left back to itself. And for y in the domain of f inverse, remember that domain of f inverse is a range of f. Domain of f inverse is a range of f. So that's why I prefer to use a y. Just for this notation. Later we will always use x if you have the domain. So f inverse of y, like you know the student number, you get the student, and then you check its student number. Of course, you get the original, right? So here, this is a composite function. This one, these two are composite function. You apply the function and the inverse function, you are back to the original input. Okay, you apply the function and the inverse function, you will back to the original input. Okay, so let's see the example. We are going to verify. So example. Verify the inverse of fx is equal to 1 over x minus 1 is f inverse of x equal to 1 over x plus 1. Okay, so how do we verify it? How do we verify it? Let's just check. I will check. By definition, whenever you have an element in the range, this is element in the range, I'm going to map it back to the starting point. Okay, so to verify one function is the inverse of the other one, you just check this f inverse of fx, see what it is. F inverse fx, this is composite function, so it's a 1 over fx plus 1. You see here, x, here is fx, so you just replace x by fx, right? And the fx is 1 over x minus 1. 1 over x minus 1 is x minus 1, and plus 1 is x. See it? You map the range back to the initial point, initial value. Okay, and then you also check that f inverse of x is also x. So you see here we use the same letter, but they mean a different thing. This x is in the domain of f inverse. This x is in the domain of f. Okay, so fx is 1 over x is here, so it's f inverse of x and minus 1. Right? Whenever you have x, you place it here. Whenever you have input, you place it here. Okay, and then f inverse of x is 1 over x plus 1. This is f inverse of x, and then minus 1. Plus 1 minus 1 cancel. This is 1 over x is x. Okay, so these two functions, 1 over x minus 1 and 1 over x plus 1, are inverse pairs. Or you can just say 1 over x plus 1 is the inverse of 1 over x minus 1. If you don't like this, you will directly say 1 over x plus 1 is the inverse of fx equal to 1 over x minus 1. All right, so just use a favorite, the sentence you like. So this is a verification process. We're going to verify if one function is the inverse of the other one or not. Okay, so in the first section, we define the one-to-one function. In the second function, based on the special property of a one-to-one function, we define the inverse of a one-to-one function. And the inverse of a one-to-one function interchange x and y positions. the output becomes input, the input becomes a output. So you have the domain is a range, domain F is a range of F inverse, and the range of F is a domain of F inverse. Interchange them. And because this is a back and forth process, so you apply F and apply F inverse, you get the original value. And similar thing happens if you apply F and F inverse, you will also have the same thing. All right? So remember that when you have a point AB on the graph of F is 1 to 1. Let's assume F is 1 to 1. This is just a condition, okay? It's not the evaluation. If a point AB is on the graph of F, then remember that inverse function will interchange A and B. The point BA is on the graph of F inverse. It just interchange them. Okay? So what is the relation? For example, let's see this. Let's use a basic 1, 2, 3. 1, 2, 3. Let's check. Assume we have a point 1, 3. This is 1, 3. Now, if we exchange A and B, we will get a 3, 1. 3, 1 is here. Let's check if we have 1, 2. 1, 2 is here. Then you interchange them, you will get 2, 1. 2, 1 is here. So what are the properties about this relation, about these pairs of points, AB and BA? They are actually symmetric with respect to the diagonal of the first quadrant. It's a symmetric. AB and BA are symmetric with respect to the line diagonal. What is diagonal? Y equal to x. This is diagonal. So that is the geometric property about the symmetric pairs AB and the BA. So for every point on the graph of F, you get the symmetric point BA, it will be the graph of F inverse. So based on this observation, we get the graph of a 1 to 1 function F and the graph of its inverse of -1 are symmetric with respect to the line y equal to x. Okay, so for example, let's just see the example. If we have fx equal to x cubed, then you can see that f inverse of x is a cube root of x. You check that they are really inverse to each other. You check f inverse of f of x is cube root of fx is cube root of x cubed. Fx is x cubed. Cube root of x cubed is x. And the other way, f inverse of x, it is something f inverse of x something cubed, right? We apply this function. And it's a cube root of x and then cubed. It is just x. So they are the inverse functions. And then if you sketch the graph, you will see that, well, it's hard to sketch it, but this is y equal to x cubed. How do I know it? You will see when x is 2, y will be 8. So it increases very, very fast. It increases very, very fast. Okay? 1 is 1, but whenever you get 2, it will be very high. And cube root of x, check this graph. Well, cube root, this is y equal to x cubed. This one. And this one is y equal to cube root of x. How do I know it's a little bit flat? Because when x is 8, y is 2, right? X is 8, y is 2. So when x is already very large, y is still very small. So here is x is 2, y is equal to 8. It will be very tall. If I sketch it carefully, you will see that this is this one. These two graphs are really symmetric about the line y equal to x. Y equal to x. Okay, so an example from the textbook. It says we let's get it. We have negative 2, 1. So 1, 2. Negative 2, this is negative 2, this is negative 1. So we have 1 point, this is negative 2, negative 1, negative 2, negative 1, negative 1, 0, negative 1, 0, 2, 1, 1, 2, 1, 2 and 1. Okay, so assume this is a graph of certain function. We don't even care what this function is. This is a graph of function. And from this graph, we know f is a 1 to 1 because you can just imagine whatever horizontal line here, you will have at most one intersection point. If it's between -1 and +1, you will have one intersection point. If it's above 1 or below -1, no intersection point, right? So you will have at most one intersection point. Now let's try to sketch the graph of the inverse function. So remember, this is segment. The straight segment is easier to sketch. For example, you have 2, 1 from the original function. Then this point, the corresponding symmetric point will be 1, 2. 1, 2. This is a corresponding point. And this one is a -1, 0. If you get the image, the symmetric image, you will get 0, -1. 0, -1 is here. This is 0, -1. It's exactly on the y-axis. X is 0, y is 1. And because here you just directly connect them, so here you also connect them. Okay? And then you check from here you have a -2, -1. Its a symmetric image will be -1, -2. Let's make this. And this point is a symmetric image of this point. So you just connect them. So this sketch, pencil sketch, is a graph of the inverse function. This pencil graph will be the graph of the inverse function. If you just have segments, it's easier to draw the graph of inverse function. If you have something which is slightly different or weird, then it's harder to sketch. It's based on your uh, ability. So for example, in the textbook, they gave us such stuff. Assume we have, well, let me try. Okay, assume, oops, it's my bad. It should not go back. It should go this way. No such part. Let me redraw it. It's bad. Okay, this is a graph, one-to-one function. This one, I drop it because if I go back, this is not even a function. Function, you will not, you see here, use a vertical line, one input you will have, I will have two outputs. That's my mistake, so it's wrong. I got this one. This one, if I want to get the image of the inverse function, I will first draw the symmetric axis, and then I will try this, try to see how. All right, so this one will be the graph of, if this is y equal to fx, this one will be y equal to f inverse of x. Or we can just say sketch, this is f inverse of x. Okay? So if we only have segments, it's easier to sketch. You just locate the endpoints and then use a straight segment to connect them. But if you have really some curves, just try your best to sketch it. Okay, so that's a graph. The graph of original function and the inverse functions are symmetric about the line y equal to x. That is the diagonal of the first and the third quadrants. Okay? Okay, so next let's see how do we find an inverse function. So we will do the examples and see the steps. Find the inverse of fx equal to 2x plus 3. All right, okay. So remember that to get the inverse of the original function, we interchange x and the y. But here there's no y, just x. So first you introduce y. Let y be fx be 2x plus 3. Okay? Remember, this is original function. And then what do? You interchange x and y. Interchange x and y, we get, see, y becomes x becomes a y. I got this one. This is a middle step. You can just ignore it, okay? You just get y is equal to 2x plus 3, and then you interchange x and y. Whenever you see y, you write x. When you see x, you write y. And then solve for y. We are going to write y as a function of x in terms of x. Well, that's the rest of the steps will be different depending on the problem, the formulas. So for example, for this one, we're going to move 3 to the other side. X minus 3 is a 2y, and divide two sides by 2, you will get x minus 3 over 2 is a y. And I write it in the, I flip the left and right side, I'll get this one. So the inverse is y equal to x minus 3 over 2. Y equal to x minus 3 over 2, and that's it. Okay, so how do we do that? The first step, we name y. Sometimes they don't give you y, you just do it. If they already give you y, you can jump to the second step. Second step, you interchange and y, get the concrete formula. And third step, you're going to solve for y in terms of x. And possibly the difficult step will be the third step because you're really going to solve y in terms of x. Different function will give you different difficulty. Okay, so different function will give you different difficulty. So you have to be able to solve certain equations. And then the final answer will be the inverse of function. Okay, so let's see another example. So for example, if we have fx is equal to 2x plus 1 over x minus 1. What is the domain of it? Domain is x is not equal to 1. Because when x is 1, the denominator is 0. Okay? So far we don't prove anything. We just assume fx is 1 to 1. Okay, so this is a if. Let's put if fx with this formula and this domain is 1 to 1, find the inverse. Find the inverse. Well, how do we do that? First, we name y. We let y be 2x plus 1 over x minus 1. We interchange x and y to get x is 2y plus 1 over y minus 1. Okay, and then solve for y. Okay, so now what do? We multiply two sides by y minus 1. Expand it, x y minus x is equal to 2y plus 1. And then I'm going to move 2y to the left side and x to the right side. So xy minus 2y is x plus 1. We factor out y, we'll get y x minus 2, x plus 1. Right? We factor out y, we'll get x minus 2. And then we divide this equation by x minus 2. So y is equal to x plus 1 over x minus 2. So in this process, or in this formula, we can see that x cannot be equal to 2. X cannot be equal to 2. So the inverse is y equal to x plus 1, x minus 2. If the question asks you, check your result, and check your result, how do you answer this part? If they ask you, I say if they ask you check your result, you will also call it f inverse of x. And then you're going to really check those two formulas. F inverse of x, see what it is. Fx is this. So it's a 2 f inverse of x plus 1 over f inverse of x minus 1. You see here, whenever you have x, you're going to copy f inverse of x because in this computation, f inverse of x is input. Okay, and then you're going to use this formula. F inverse of x is x plus 1 over x minus 2. So it's 2 x plus 1 over x minus 2 plus 1 x plus 1 x minus 2 and minus 1. Okay, and then you simplify it. How do we simplify it? Its difficulty comes from this denominator. So we multiply top and bottom by the denominator. So x minus 2 cancel with x minus 2. So you only have 2 times x plus 1. This is 2 times whole thing. And 1 times x minus 2. Here, x minus 2, x minus 2 cancel. This is x plus 1 minus x minus 2. Okay, whenever you see minus and the two term, more than one term, you are going to put parentheses. That's all. Continue the simplification. Continue simplification. Okay, so here the numerator is a 2x plus 2. So 2 times x, 2x, 2 times 1 is 2, plus x minus 2. Denominator, x plus 1 minus x and plus 2, minus x and plus 2. So 2 canceled, plus x minus x canceled. You will get 3x over 3 is equal to x. See it? So it satisfies the condition. And the other one, f inverse fx, we're going to do the similar steps. So f inverse of x, here's f inverse of x. You have x plus 1 over x minus 2. So just put input in the position of x. And fx is 2x plus 1 over x minus. Right? And then we're going to multiply top and bottom by x minus 1. So it is, you cancel x minus 1 here, you get a 2x plus 1 and plus x minus 1. Here, it's a 2x plus 1 minus twice of x minus 1. So this x minus 1 canceled, minus 2 times x minus 1 is here. Oh, let's continue simplification. It's a 2x plus 1 plus x minus 1. Here's a 2x plus 1 minus 2x and plus 2. So 1, negative 1, 2x minus 2x. So you get a 3x over 3, the same x. So after you finish this, so we checked our result. We checked our result. These two conditions guarantee that our computation is correct. Okay. One more example. We know that y equal to x squared is not a one-to-one function. But if I restrict it to negative part, if I only use this part, it is a one-to-one function. And then how do we get the inverse? So similar thing here. Because you already have x and y, so I'm going to interchange x and y. We'll get x equal to y squared. And then we're going to take square root. Remember that your x actually give you the, you see, x position is a y position. So here your y is less than or equal to 0. When we take square root, you have to guarantee that your y is less than or equal to 0. But square, only square, it is greater than or equal to 0. You need to pick up the negative square root to guarantee that your y is less than or equal to 0. Okay? So this is the solution, is the inverse. Y equal to negative x is the inverse. Is the inverse of y equal to x squared, x less than or equal to 0. All right? So it depends on your domain, your definition, the domain, the restricted domain. For example, if I do not pick up this left side, I pick up the right side. If I pick up this part, I interchange x and y, we will get the same thing. X is equal to y squared. And in this case, the y is greater than or equal to 0. Y is greater than or equal to 0. You can directly apply the square root. Right? This case, y is greater than or equal to 0. They match perfectly. So this is the inverse of y equal to x squared. But here, we get a restriction, different. This is difference. Check here. So when you have the original restricted domain, you possibly, I'm not saying always, but you possibly will have different choice. For different domain, you need the different choice. Just be careful about this type of problem. All right? So this section is long, but I believe it was discussed before in the pre-calculus 1. So do the exercise. If you have any questions, send me message, email. Thank you very much. We finished this video.